quantum computing. And so we are very glad to welcome Omar Fawzi, professor at Ernest de Lyon, and also médaille de bronze from CNRS in 2019, who is specialized on so computer science and particularly quantum computing. Omar, thank you for accepting our invitation to give this talk. The floor is yours.
Okay, so yeah, this mic. Okay, good. This one I opened. So, okay, can you hear me well? Okay. So yeah, so thanks a lot for the invitation. So I don't work on AI at all. I work only on quantum computation. But I think, as you might have heard, we're seeing recently some like very important advances in terms of quantum hardware, where we start seeing really things that we cannot, like computations that we don't know how to simulate classically. And so I think there is room for very interesting interactions between machine learning and quantum computation. Okay, so what I chose to do in this talk is I'll give you a brief history of quantum computing, and then I'll try to focus on the mathematical model, right? So it might be a bit more mathematical than the other talks, but I think it's useful so that we discuss in a bit more detail about the model. I will try to define what a quantum computation is mathematically. Okay, and so and talk a little bit at the end about quantum simulation, about maybe the main potential applications of quantum computers. So, yeah, it's on. This works. Maybe I'll just use my. So now I have to do that. Yeah. Okay. Cool. Okay. So yeah, first first overview slide on what quantum information processing is before getting into the history. So at a very high level, the idea is to exploit quantum theory at really the fundamental level, not just at the technological level where we use it in order to build the devices that do computation, but at the even very fundamental level. Okay, and so yeah, before talking about what a quantum computer is and the basic building block of it, let me say what a classical computer is. And so here I'll take an abstract point of view without getting into the physics of what is actually doing the computation. And the reason, or let's say one of the reasons we can talk about classical computers abstractly is this so-called, sometimes called strong church-Turing thesis. Okay. Which says that basically any physical computation that we can do in the real world can be simulated, okay, with a reasonable overhead by some specific mathematical model, which is the Turing machine. Okay, so this thing is not a theorem, it's not a mathematical theorem, it's a statement about physics or about the real world where we live. And yeah, it just says that if I want to say something about computation in the real world, then these Turing machines or other equivalent models are good enough, and they capture this notion of computation and also the notion of speed in computation. Okay, and so as I said, this is not a theorem. It's a theorem for if you fix a specific model. So if you mathematically define another model, like your favorite model of computation, for example, let's say cellular automata, then you can show that indeed you can simulate the computation that is done by cellular automata by a Turing machine. Okay, but in general, it's just you can think of it as a hypothesis. Okay, so now getting more into closer to quantum computer, and so I want to say that the basic building block of a classical computer is what we abstractly call a bit. Okay, which is now if I want to implement this physically, I can use any physical system that has two levels which I can distinguish perfectly, okay, or easily, let's say. Okay, so this can be really any system. So it can be electric, magnetic. So it can be a capacitor which is charged or uncharged, etc. It can even be mechanical. Okay, so here I even put a picture of a Lego Turing machine that was built by the students at ENS Lyon. So yeah, so just to emphasize that the physical carrier of information is not really important when I'm making a distinction between classical computers. The important thing is that I have these two distinct levels. Okay, so what is a quantum computer now? A quantum computer, this basic building block now will be replaced by, instead of just having two distinguishable states, okay, I will have a two-level quantum system. Okay, the two is not particularly important here. If it's another number, it would work as well. But the important part is that it's a quantum system. Okay, so I look at a system which has also two distinct levels, but it's a quantum system, and so we know that the way to describe it is different from just having these two possible states, but it is described by quantum wave function. Okay, so abstractly, okay, if I abstract away the physical system, I will call this a qubit. Okay, so and mathematically we'll get into the math in a few more slides, but the basic idea, as you probably most of you would have heard, that it allows superpositions. And so the famous illustration for this is the so-called Schrödinger cat, okay, which is in a superposition of like these macro states, okay, so dead and alive in this case. Okay, and so the reason we single it out from classical computers is that, as we'll see, this notion of computer, it challenges this thesis that we described at the beginning, which is the fact that you can simulate with polynomial overhead any computation in the real world by Turing machine. Okay, so this was my introductory slide. So let me just do a very brief history with just a few selected highlights on how quantum computers, how the idea of doing quantum information processing came about, and a few highlights that I select for this talk. So probably the first people who talked about quantum computers, it's at the beginning of the 80s. Okay, and so it's often attributed to, I mean, yeah, so there's these three main people, Benioff, Feynman, and Manin, who at the same time roughly came up with the idea of put forward the idea of quantum computers. Okay, but let me focus maybe on Feynman particularly. And the point of view of Feynman was he was asking about the question of simulating physics. Okay, so he asks, when can I simulate physics with computers? And so now physics at the fundamental level is quantum mechanical, right? So if you want to simulate physics, it really means you want to simulate quantum physics. Okay, and if you know a little bit about quantum physics, it seems quite difficult to simulate a quantum mechanical evolution on a classical computer. And so this led him to propose this. So he even called it quantum computers. And he refers to quantum computers as universal quantum simulators. Yeah, and so he asked exactly this question. So can you do it with a new kind of computer, a quantum computer? Okay, so this is where this idea started, is with the idea of really simulating quantum physics. Okay, if you want to simulate quantum physics, you better build a machine that uses the same physics as the underlying building block. Okay, so then I want to mention this first, I think, important idea which came about a few years later here in the 80s. So this is not about computation per se, right? This is just about information processing. But I think this is really, as far as I'm aware, this is the first application of quantum phenomena for an information processing task in general, which has nothing to do a priori with quantum physics. Okay, so I mean, the person which came up with the basic idea is Wiesner. He came up with this idea of quantum money, but maybe the most famous application is due to Bennett and Brassard, who they came up with a protocol, okay, for doing so-called key distribution. Okay, so this is a protocol where you have two parties. Let's call them Alice and Bob. They communicate quantum particles, okay, using a predefined protocol. And at the end of this protocol, both of them share a key, okay, which is guaranteed to be private information theoretically, right, without having to use like hardness assumptions. And yeah, so this is an application. So a priori, this has nothing to do with quantum mechanics, but it exploits the properties of quantum mechanics to achieve this key distribution. Okay, and so if you're familiar a bit with quantum mechanics, the main thing at work here is the uncertainty principle, right? The fact that you have complementary observables, okay, that cannot be measured at the same time. Okay, and so one thing I can mention is here, this doesn't need a full quantum computer. Okay, so this technology here for key distribution, this protocol is relatively simple. It needs relatively simple quantum devices. And so this is actually can be implemented, right? And there are a few companies that do that and sell these devices. So in particular, one of them is ID Quantique which is based in Switzerland. Okay, so this is one application, again, not in quantum computing per se, but an application in cryptography. Okay, so perhaps maybe the biggest breakthrough in the area is due to Shor, right, which was building on previous work by other people. It came in 1993, 94, and so he designed an algorithm, a quantum algorithm. Okay, so at this level, it's all theory, right? So he like using the laws of quantum mechanics, he designed a fast algorithm for factoring. Okay, so I think this is interesting for at least two reasons, right? So the first reason is that, again, this is an algorithmic problem which has nothing to do a priori with quantum mechanics, right? So this is the problem of given a number, right, which is, let's say, a product of two primes, is to find these two primes. Okay, so the problem of multiplication is is simple. I mean, you can do it efficiently, but going back from the multiplication of P and Q to P itself and Q itself, this is a problem which is algorithmically hard for classical computers. And so Peter Shor came up with a quantum algorithm that would do this in a time which is polynomial in the number of digits of your number. Okay. Yes. Yes. Yeah. Now this, of course, needs a quantum computer. It's unlike this application, which doesn't need a full quantum computer. Now this needs a full quantum computer. Okay. So the second reason I think this is quite important is that, okay, so first of all, you might think, okay, the factoring problem, who cares? This is just a random math problem. But actually, the hardness of this problem is at the basis of really most of public key cryptography, right? So this has strong consequences in terms of cryptography itself. So if we can build quantum computers, then large-scale quantum computers, then we can break really most of public key cryptography. Okay, and so of course this led to now people trying to move away from factoring, and this is the whole area called post-quantum cryptography. Okay, this is not quantum per se, but it's called post-quantum because it's supposed to be resistant to quantum attacks. Okay, so this is Shor, and then the last sort of milestone I wanted to present is something you might have heard of. It happened a few years ago. Now this is actually experimental. Okay, so this is the first one. This is all theory. It was all theory. Here, this is in 2019. This Google, they built a quantum machine, okay, which has 53 qubits. Okay, so it's a quantum device. And so what they did, okay, why? I mean, people were building quantum devices for a long time. Why was this particularly important? Is because they achieved what is called supremacy in the area. So what do I mean by supremacy? The question here is to solve a task, a computational task. Okay, it doesn't matter if it's not important, if it's not relevant, but just to solve any computational task that we cannot do with today's computers. Okay, even with big computational power. Okay, so here they defined by themselves a computation. Okay, so here it's a sampling problem. Okay, so they want to sample from some distribution, And so they sampled from some distribution, and they estimated that if you want with classical computers to sample from the same distribution, you would need a few hundreds of years. Okay, so this is so really, and the reason we came up with this only at in 2019 and not before is that okay, is that around 40-50 qubits is really where the exponential of this number starts being really too large for a quantum computer, for a classical computer. Okay, this is where we start. Yes.
Computer, then you can maybe program other tasks in this computer.
Yes, this computer, you can program it. Yes, you can apply arbitrary gates.
So is it sufficient to run, for example, Shor?
No, it's not sufficient at all, right? So
what is the size? How many qubits do you need
to run Shor's algorithm?
Yeah.
Yeah. So okay. So I think this I had it after. So I'll comment on it on this slide exactly. So yeah, that was it for the history. And so yeah, you can ask. Yes, sure. Okay.
How do you define the supremacy? It can solve a problem that a classical computer can solve in what's limited time?
Yeah, so this is, I mean, it's in reasonable time with today's computing power. Yeah, it's not. Yeah, I think they estimated to, I think, 10,000 years there. I mean, but of course, I mean, these things are heuristic, right? Because we never know what is the best algorithm. Actually, as I'll mention, this has now been done classically, right? So, so like a few years later, people managed to get samples from this same distribution with the same accuracy and with better even accuracy by just developing better and better classical algorithms. Okay, so yeah, so again, all these, I mean, usually when I talk about something not being possible on a classical computer, this will never be provable, right? Because I mean, otherwise it will prove P different from NP in particular, right? So yeah, proving that there's no efficient algorithm for a given problem, this is in general very hard. So we usually only do this provided we have some, I mean, by assuming some complexity theoretic conjecture. Okay, good. Okay, so all this is nice, but okay, why is it so difficult to build these quantum computers, and why we don't have computers that for example, that run Shor's algorithm? And the difficulty is that yeah, so when you try to construct a quantum mechanical device which behaves really quantum mechanically, there's various sources of imperfection that come in, and the main one perhaps is decoherence, right? So the systems tend to become classical, and so you lose these beneficial quantum effects. Okay, so and actually this was I mean, when Shor's algorithm came out, people said, yes, this is nice, but this will never be able to do this in practice because this algorithm is very sensitive to noise. Okay, and so in practice we'll always have a little bit of noise, and so this is not physical. I mean, in the sense that Shor's algorithm, yes, it does factor quickly, but it's not a physical computational model that we can have in the real world. Okay, so, and so soon after Shor's algorithm, people started thinking about error correcting codes, right? So can we make this algorithm robust? Okay, so of course here it was an algorithm which was assumed to be perfect. Now what happens if everything in my quantum algorithm is imperfect? Okay, so people started thinking about error correcting codes and fault tolerant quantum computation. Okay, so it only took a few years before people proved an actual fault tolerant theorem, okay, which says the following, that it is possible, so it's possible to take an ideal computation, an ideal quantum computation, okay, so for example, Shor's algorithm, okay, and to transform it into another one, okay, and this new one is robust to errors, okay, so it's robust to errors, of course, provided the error rate is sufficiently small. Okay, so that's why people are trying very hard to get below this threshold rate because we know that if we go below this threshold rate, then we'll be able to do arbitrarily long quantum computations. Yes, there was a question.
What is the sufficiently small, like with respect to the number of qubits?
No, this is independent of the number of qubits. It's a specific number. It depends on exactly your model of error. But let's say if you, yeah, no, this is a fixed number. Like and these are, okay, here, these are estimates. It depends on what you have provably and what you have with simulations. But okay, so the theorem here says that if the error rate is, I think the theoretical estimations are not very good. It says that if you have an error rate that is below 10 to the minus 5 or something, then you know you can do arbitrarily long computations by just making your circuit a bit larger, right? By compiling your circuit, we have a fixed method to transform your circuit into a larger one, such that if the error is below this error rate, then at the end, the result of your computation will still be correct, okay? But then, of course, this is what we can do provably, that you can do simulations and check what works. And you observe in this case is that you can actually go to a little bit higher error rates, okay? So, yes.
What is the origin of noise?
Oh, I mean, this is really dependent on the specific architecture. But so, okay, if I talk at a high level, it's very difficult. Okay, so you want to build, so you have two contradictory things you want to achieve, right? You want, at the same time, you want to isolate your system from the environment so that it keeps the quantum mechanical effects. But if you just isolate your system, you won't be able to do computations, right? So you want to do I mean, you want to say that when I apply a specific gate, I act on a few of my qubits and I rotate it. So you have to interact with the system, okay? And so if you interact with the environment, then some quantum behavior will disappear. This is what is called decoherence. So I would say, yeah, just to summarize, it's the interaction with the environment, the main source of imperfections. Yes.
If you want to do this at the virtual level with the like simulations,
yes,
isn't it easy to like you have just Schrodinger equation to solve?
Yes, yes. So I will maybe it will be simpler to answer your question once we get into the math, because yes. So yeah, so this is just to say that in theory, this is possible. So it's possible to perform this computation. You just have to go below this error rate, okay, and be able to construct systems which, of course, it has to be that as your system is bigger, your error rate stays at this level, that it doesn't grow with your computation. But provided this is possible, then we know this is quantum computation of arbitrary size is possible. Okay, so yeah, so this was about noise, and yeah, just the thing is that you can actually run some small and noisy quantum computations if you want. I mean, almost all the big companies, they have their you can access some of their quantum devices and run some of your computations. I put a few examples here. Yeah, so for example, on AWS, you have even several companies that you can say, I want to run, for example, on the IonQ computer, which uses some technology, and some others which use another technology, etc. Okay. So yeah, some of them are small, some of them are very specific for some. So D-Wave has a very large quantum device, let's say, but that is very specific, that only solves specific kinds of problems. Okay, good. So now I'll move to the board and do some math. I'm not sure this is very visible, but it looks okay. So yeah, so now let's get a little bit into the details of what the mathematical model is for a quantum computation. Okay, so let's start with 1 qubit. Okay, so the state of 1 qubit is just described by a unit vector. Okay, so, and I'll be using this useful ket notation here. Okay, so you can think that if I have a classical system, I have 2 possible states. I call one of them this ket 0 and the other one ket 1. Okay, so the only difference for a qubit is that I have all the possibilities of alpha 0 plus beta 1, where alpha and beta are complex numbers and their absolute value squares sum to 1. Okay, so the alpha and the beta is called an amplitude, and their absolute value squares are probabilities. Okay, so the reason they sum up to 1 is I can interpret them as probabilities. Yes. So alpha is a complex number. Oh, what's the meaning of this? So think of it as just a vector. Okay, so this is a basis element, and this is a basis element. So, I mean, you can think of it as just a vector with coefficients alpha and beta. This is just a vector. Okay. Okay, so this is 1 qubit. And indeed, if I measure this qubit, I will observe 0 with probability absolute value of alpha square. And if I observe 1, I observe 1 with probability absolute value of beta square. Okay, so if you have just 1 qubit, it's not very interesting for quantum computing. So the interesting thing is when you start putting lots of qubits together. Okay, so then the state of an n qubit system is really an arbitrary superposition of all the possible states of it's an arbitrary superposition of bit strings of length n. Okay, so x is a bit string of length n. Okay, and I put a coefficient in front of every bit string. Okay, and also same thing, I have the sum of the absolute value squares is equal to 1. Okay, so a very specific case when I have a classical state, it's just that one of these alpha x's is 1 and all the others are 0. Okay, and so the important thing to notice here, and this may be the most important message of this talk, is that which I'm sure many are you already aware of, but which is the fact that if I want to describe the state of a general quantum state on n qubits, I need a priori to store 2 to the n complex numbers alpha x. Okay, so even if I want to track for later, if I want to track a quantum computation, if I just want to say, okay, what is the state of the computation here? Even just to store that, I need exponentially many numbers in general. Okay, and this is, if you want, this is the source of the quantum speedup that you get, and which is the same exactly as the source of the reason that Feynman was saying it's difficult to simulate the quantum system in general. Okay, so now this was just about states, but I want to talk about computation. So if I want to talk about computation, I have to tell you how we transform these states. Okay, so what I will do first is I will tell you what an operation, I'll restrict myself to 2 qubits for now. Okay, so I take 2 qubits. Okay, so 2 qubits means n equals 2 here. Okay, so the state space for this is 4-dimensional. Okay, and so the valid operations on 2 qubits are just given by linear operations that preserve this property, this normalization property. Okay, and so this is just called a unitary matrix. Okay, and so a specific example is such a unitary matrix, for example. This is what does C naught, for example, controlled on the first qubit, I do a C naught. And so you see here that I can apply it on an arbitrary 2 qubit state, like for example, this one. I should have put the parentheses here. Okay, so if I apply it, for example, on this state, I get this corresponding state by linearity. Okay, so it maps states on 2 qubits to potentially different state on 2 qubits. Okay, and it acts linearly, so it suffices to specify it on a basis. So this one, yes, so that's why I said I missed to put parentheses here. Yes, I should have done this here. Yeah, there's parentheses. Thanks. Okay, so now I can tell you what the quantum circuit is. Okay, so let me start first pictorially by saying what the quantum circuit is, and then I'll give a slightly more formal definition. So it's as you might expect, right? As a classical circuit, you have a bunch of wires, you have n wires. Each wire has is in a given state, right? It's a bit 0, 1, and you keep applying gates, like for example, and or, etc. Now the difference is that gates, instead of being and or, they're just unitary matrices on the space of 2 qubits. Okay, so exactly here I put an example where I have a computation on 4 qubits, and so I start by applying a unitary matrix on the first 2 qubits, and I leave the other ones as they are. Okay, and then I apply on 2 and 3, etc. Okay, so I think this is quite intuitive, and so yeah, if I want to be a little bit more formal here, so because I think yeah, it's useful to. So yeah, so let me try to be a bit more formal. So a gate, right? So I see a circuit will be just a sequence of gates, and a gate is given by 2 things. First, on which qubit it acts. So it's a pair I and J. Okay, these are numbers here, for example, to be 1 and 2, and also what is the unitary matrix that I want to apply. Okay, so this is a 4 by 4 matrix. Okay, so. Yes, so I mean, what is crucial is that it's on a constant number of qubits. That's not on everything, because then, I mean, the whole notion of computation is about saying that I can act locally between 2 of the qubits, and I compose them together, and globally I get a total unitary, right? So, I mean, it's like a classical circuit, right? So a classical circuit is just about, it's about like, how do I compose local operations, in the sense that there, for example, it's an and between a few bits, or an or between a few bits, and overall I want to do a useful computation. And so here too, it's a way of, if you want, composing very simple unitaries, which are of this form, in the sense that they act as the identity on almost all the qubits except a few of them. Like here I took an example of 2 because this is enough, right? Because it's the smallest, which is enough. And yes, and it's universal in the sense that I can achieve all possible unitaries as a multiplication of such unitaries of this form, right? So this is a theorem. It's not too hard to show that you can get all unitaries in this way. And so, I mean, I guess you can see, for example, why 2 is necessary. If you started with just 1 with unitaries acting on 1 qubit, then you'll just get product unitaries, and it's obvious that you won't do it. You won't get everything, right? So, but 2 is enough to get everything. Yes. Okay. So here, yeah, just a small thing is that here I took the setting where V is an arbitrary matrix. You can also fix it from a finite set of gates. That also works, and that's also universal in approximate sense. But for simplicity, let's just say that we can apply an arbitrary unitary on 2 qubits. Okay. So here. As I was saying, so a gate is given by just these 2 qubits on which we act together with a small such unitary. And what is the unitary that is computed by the gate is just this unitary on just I and J tensored with the identity everywhere else. Okay, so I do nothing on the rest, and I do this V on I and J. Okay, and so now if I'm given a circuit which is a sequence, an ordered sequence of gates, it defines a unitary matrix, which is just the product of the unitaries corresponding to each one of these gates. Okay, so again, yeah, I want to stress that the circuit defines a 2 to the n by 2 to the n unitary matrix, okay, which is obtained by these simple unitaries, right? So each one of these U's is quite simple, right? It's just acts on just 2 of the qubits, and on the rest it does nothing. Okay, but the idea is that by combining the gates and multiplying these unitaries together, you get a unitary which hopefully computes something which is of interest to you. Okay, and this is just, if you want, this is what a quantum computation is. It's just the multiplication of such structured matrices, of huge such structured matrices. Yes. Mm-hmm.
Do you predefine the V, the operation, or do you learn it?
So no.
The operation that acts on the...
So this is, I mean, this is the choice of the algorithm designer, if you want. So he can choose arbitrary V's, and this, I mean, the specification of the algorithm, it's a, I mean, as you notice here, it's a very low level specification of algorithms in the quantum case. Yeah, we don't have, I mean, yeah, this is, I think one reason we don't have lots of quantum algorithms is it's quite difficult to reason about them because they're super low level. I mean, it's as if you were designing algorithms by describing your algorithm with ands and ors, right? So this would be quite difficult. And so, yeah, we have to reason with this model because we don't have a better way of reasoning about it. And yes, so the algorithm designer should provide these, yeah. Okay, so yeah, so just yeah, to be a bit more explicit, what is a computation in a quantum circuit? So yeah, given a circuit, as I said before, it's a sequence of gates. So on input X, okay, so now suppose I want to do a classical computation. Okay, so I take an input X, which is a bit string of length n, and what classical computation does my quantum computer do? Okay, so it's a probabilistic computation in the sense that it will output a bit string y on input X. Okay, so this is a probability. And so to get this probability, I just have to look at a fixed entry of this unitary matrix, okay, which is, I look at the row and column, which are indexed by X and Y. Okay, this will give me a probability. Okay, so for example, just as an example to make things a bit more concrete, so we can say that the circuit C computes a given function f, okay, from bit strings of length n to bit strings of length n, if, for example, the probability that my output is f of x on input x is bigger than 90%. Okay, so some comment I want to make because I think, yeah, we heard a lot about tensor contractions and tensor operations, let's say. So you can view actually the computation of these amplitudes as a tensor contraction problem, right? So you can take your circuit, right? You can put a small tensor here, okay, which corresponds to the bits of x, okay, so which you choose as a function of the bits of x. So this will be tensors which are like of rank 1, so there will be vectors. Okay, and you just, okay, so this amplitude, this number, okay, you can obtain it by contracting this tensor. Okay, so if you contract this tensor, you get a number, okay, a complex number, and if you take the absolute value square, you get the probability. Okay, and so this is to say that you can, in some sense, view like simulating a quantum circuit as contracting a tensor network. Okay, and actually, so remember I mentioned that in this Google supremacy experiment, there was a classical computation that achieved a similar performance. They did it using tensor contraction methods, right? So they used the advanced tensor network methods in order to contract the corresponding tensors of the circuit that corresponds to the Google experiment, and yeah, they were able to get samples that even have a higher accuracy than the Google experiment. Okay. And I think, okay, I don't remember the exact numbers, so of how many GPUs they used, of how many hours. I mean, it's not, of course, a trivial computation. They used, I think, hundreds of the order of 100 GPUs. I don't know for how long exactly. I don't remember. Okay, so yeah, okay, so let me summarize this. So at the mathematical level, quantum computation is just, you can see it as a multiplication of very large structured matrices. Yeah, so if you want to simulate it classically, then you have to do this tensor contraction. But if you have actual quantum devices, then these are things you can implement with a number of particles, which is just proportional, or which is just equal, let's say, to the number of wires that I have here. Okay, and so that's why in settings where the tensor contraction is very expensive, it's useful to have a quantum computer because it gives you this result. good. So I'm not sure in terms of time. Yeah. Okay, so I wanted to finish with discussion of probably I think what the applications which are likely to have the most impact, the applications of quantum computers which are likely to have the most impact, which motivated quantum computers is quantum simulation. Okay, at least for now, right? So there is still research going on. It could be that one finds even more important applications, but at the current state, I think quantum simulation is probably the most important application of quantum computers. Okay, so we heard a little bit about quantum simulation already in a few talks. And now I'll try to talk a little bit about it in slightly more mathematical terms. Okay, so what do I mean by quantum simulation here? So I mean, it's a very vague term, but in this talk, let's say, it's defined by taking a physical system of interest, which I'll model by a Hamiltonian. Okay, so this is a Hermitian, also very big matrix, 2 to the n by 2 to the n, but it's very structured. Okay, in the following sense, in the sense that it's a sum of terms which act on, let's say, nearest neighbors. Okay, so again, I can think of having a lattice on 2D, for example, of spins here, and I have these Hamiltonian terms which govern the interaction between nearest neighbor particles. So here I have particle I and j, so I have a Hamiltonian term for ij. Okay, and so this is a very physical assumption, let's say, to assume that it's a sum of local terms. Okay, so depending on the specific models, you can assume it's on a lattice, or it has arbitrary interactions between faraway elements. But the most physical, probably for most applications, yeah, being in a lattice in 2D or 3D is an interesting case. Okay, and so I want to talk about two typical questions of interest in this area in general called quantum simulation. So the first class of problems, or the first kind of problem that is studied a lot in many body physics, let's say it's the problem of computing the ground energy. Okay, and so this was exactly the question that in this density functional theory talk that we had a few days ago. And so the question here was, given this H, okay, I want to determine the minimal eigenvalue. So the value of the minimum eigenvalue of this huge matrix H. Okay, so the thing I'll say first is so this is a well-defined computational problem. Given as input H, I want to compute this number, which is this minimum eigenvalue. Okay, so it turns out that in general, the complexity of this problem it's very hard, right? So it's easy to see actually that in such problems you can encode typical constraint satisfaction problems like SAT or related problems. And so this problem is in general NP hard, and it's even harder than that. It's QMA hard. Okay, so QMA is a quantum version of NP. Okay, so it's quite unlikely that there is even a quantum algorithm that runs in polynomial time for all H that computes this minimum eigenvalue. Okay, this is a very hard problem. Okay, so of course this is a complexity theory statement. It's not about something in practice. So it could very well be that for Hamiltonians in practice that are of interest, one can compute this value, but this is just a generic complexity theoretic statement. Okay, so yeah, in addition to this complexity theoretic statement, yeah, we can ask that in practice, are there prospects for quantum computing helping in quantum chemistry? Okay, so if I take a typical molecule, for example, that is studied, let's say, in quantum chemistry, do we have evidence that if we had a quantum computer, we would get a very large speed up compared to the current classical methods we have in quantum chemistry? And yeah, so there was this very recent, quite long study by researchers from Amazon and Caltech together with leading quantum chemists. And they studied this question in detail. And it turns out, unfortunately, that there is no strong evidence so far that we will get an exponential speed up in quantum chemistry using quantum computers. Okay, so that, yeah, if you study things in more detail and study in detail the classical algorithms, there is not yet exponential evidence for exponential speed up. Okay. Again, it doesn't mean that there are no polynomial speedups, and we have some evidence for that there are some interesting speedups in practice, but they're not like the usual exponential speedups that we like. Let's say, for example, in Shor's algorithm, where the best classical algorithm is exponential, but the quantumly we can get a polynomial time. Okay, so for these ground states, for this ground energy problem, these are very hard problems for which probably we might have some quantum speedups, but it's not clear yet that it will be a huge speedup. Okay. Now, so let's look at the second class of problems in simulation, which is closer to the word actually simulation. This is the word dynamics. Okay, so imagine that I have a system, right, which is governed by this Hamiltonian. I want to know, and it's prepared in a simple state. Okay, so it's prepared in some product, very simple state, and I let it evolve in time, and I want to know after a given time what is what are some properties of this state. Okay, so and this is what I try to describe here. Okay, so this problem is, yeah, given a Hamiltonian and some time t and some observable. Okay, the exact technical details here don't matter, and I would like to compute the expectation value of this observable with respect to the time evolved state. And now this problem is this can be done efficiently on a quantum computer. And so if you think about it, a quantum computer is basically doing that, right? So basically a quantum computer, what it's doing is it's simulating a quantum evolution. Okay, it's not an evolution by time-independent Hamiltonian, but it is, I think, not surprising to see that a quantum computer would be able to do this efficiently. Okay, and this is what even Richard Feynman suggested in his 1980 paper, and this was done more rigorously in this in the 90s by Seth Lloyd, Universal Quantum Simulators. It was studied in a bit more detail, and then there is lots of subsequent works which do this more and more efficiently as a function of the number of qubits and the time you want to evolve the Hamiltonian form. Okay, and so this can be solved efficiently on a quantum computer, like so in time which corresponds to which is proportional, let's say, to the number of qubits and also to the time you need to evolve your system for.
Yeah. The inverse of the number of qubits. This number of particles or the
number of qubits.
So the time should be inversely proportional to the number of qubits per system.
No, I mean it's of course the larger the system you want to simulate is, the harder it is to simulate, the longer time it will take.
So you have the same number of particles that you simulate, that the ones that you use in your computer?
Yes, yes. Yeah. Of course, it's similar, and it will be more typically, of course. So yeah, you want to simulate a system of 1,000 qubits. You will typically use, okay, depending on the specifics of the quantum computer, you'll typically use more than 1,000 qubits, because you have to transform from the Hamiltonian of interest to your quantum circuit, and this will incur an overhead. And yes, it will also depend on the time needed. So it's natural that it increases with n and t. Yes. I mean, yes, and of course, okay. So this is what can be achieved on a quantum computer, and of course, the best generic algorithms, the best generic classical algorithms we have for this problem, they scale exponentially in n or t. So yeah, of course, yeah, this is a typical problem. The problem of dynamics is really the problems for which quantum computers are really significantly better than classical computers, again, as far as we know, right? I think this is where one should look for interesting problems, interesting applications of quantum computers. And actually, okay, maybe let me not mention. Okay, let me just summarize. Let me just summarize that quantum computation is what the quantum computation is mathematically is, as I said, it's you take very structured matrices and you multiply them together, and this defines to you what a quantum computation is. Yeah, and I said, so, I mean, one of the potentially biggest applications of quantum computers is quantum simulation, and in particular, simulating the dynamics of a quantum system. Okay, and so I said also that for ground state problems, like for determining specific, so the ground energy, let's say, or ground state properties, the problem is in general hard. We have some evidence for quantum speedups, but not necessarily conclusive. Yeah, here it's not very visible, but yeah, I wanted to mention just here that this survey paper called Machine Learning and Physical Sciences, actually Laurent is one of the co-authors of this, and so it has a few sections on quantum computations, on quantum computing and machine learning. Okay, so for example, it has a full part on many-body quantum matter, how you can use machine learning methods to solve these many-body quantum problems. There is also, yeah, to help quantum computing. So there's many like multiple techniques that use machine learning in order to help you, for example, perform error correction. Okay, so as I told you, for error correction is a big issue in quantum computing. You have to constantly be able to correct for errors. And if you want to do that, to be able to do that efficiently and to search for good error correcting codes, then people have tried to apply machine learning to that and even use it for experiments sometimes. Yes, here also quantum chemistry, and maybe, okay, let me just end with a question that we can maybe have in the brainstorming session. Is that as far as I have seen, so you see this Google supremacy experiment. Now there is a classical way of simulating this using tensor networks. As far as I'm aware, there has been no trial for using machine learning to simulate the outcome of a quantum circuit, right? So you can say that I want to build a machine learning model which takes as input a quantum circuit and outputs samples from the output of this quantum circuit. As far as I'm aware, there is no significant works, at least on this. And maybe one thing also one could exploit here is that, of course, when we implement quantum circuits on real quantum hardware, it will always be noisy. And so in general, when it's noisy, it can be a little bit simpler to simulate. And so maybe this noisiness can also help can also make it simpler, let's say, to have the machine learning model simulate these noisy quantum circuits. And so, yeah, it's just an open question, and let me end here. Yeah.
Question: why is it difficult to use machine learning to simulate the quantum circuit? If you have, so do you mean the design of the circuit? Because if you design the circuit, then it's just about probabilities and compositions, right? So can you expand a little bit on that?
Sure. So, so again, here you want to simulate from. Okay, so let me. So I mean, here you would want a machine learning model which takes as input a quantum circuit. So, for example, it would take as input this thing, so the list, the description of this unitary, this one, and the fact that it acts on 1 and 2, etc. And let's say we fix the input state to all zeros. Okay, and it would have to sample from this output. Okay, so this is exactly what the quantum computer would be doing, right? So quantum computer, when you measure it at the end, you will find this y that follows a given distribution. Okay, so if on a classical computer, sampling from this y is in general, okay, we don't have a way of doing it provably in general. Okay, but what I'm saying, I mean, the question I'm asking here is, okay, of course, what one could do is one can look at small circuits of small size, let's say 10 qubits, 20 qubits, 30 qubits even. And in this case, one can do this computation. It's not 2 to the 30, it's not 2 to the 20, it's not too big. And one can get such samples, okay, as a function of the circuit. And then one can train the model on this data which is generated, and then try to apply it on larger circuits. Okay, and then, for example, one specific thing one could do is one can look at this Google supremacy experiment, and okay, so they have some quantity that they compute given the samples, because right, you don't know what the distribution is, right? Because this is a problem which is hard. We don't know how to do it on a classical computer. So they did something called cross entropy benchmark, which you can compute using your samples. And so one could also do it. I mean, if one has such a machine learning model, one can just output the samples and just compute this cross entropy benchmark, and maybe one can achieve a similar performance and better performance than what Google does, than what the Google quantum computing does. Yes.
For this example, you have used 2 qubits.
Here?
Yeah.
Yes, I mean, there's 4 qubits in total, but this is always the case that the gates, they act on only 2 qubits. It's only, I mean, this, you can think of it as the definition of the model, okay, is that I always act between 2 qubits and not on the whole thing.
And inside of the gates,
there is, I mean, this is specified by some unitary transform, by this matrix, which I called V here. So it's, if you want, it's specified by 16 coefficients, okay? And given these 16 coefficients and the gates on which you act, this would specify the box. I mean, I didn't write anything in the box, but yeah, if you want to specify fully a circuit, you would have to give for each box what is the corresponding 4x4 matrix that you want to apply. Yes, if you want, this is the, I mean, if you want to relate it to classical circuits, it would tell you whether this, I should apply an AND gate or a NOT gate or one of these. It will tell you. So as I said, so it's possible also, I mean, I did just here for simplicity, it's possible also to restrict yourself to a finite set of unitaries, like 5 or something. And so there's 5 possible unitaries. In each position, you apply one of these 5, and that's it. Okay, so in this way, this model will not be exactly universal in the sense that by multiplying elements from this set of gates, you won't get all unitaries exactly, but you can get arbitrarily close to any unitary. Okay, but with this model, you can get exactly any unitary if you want.
My last question is about the Hamiltonian. Is there some practical interpretation?
Yes, practical interpretation. Yes, I mean, if you have, let's say, a material or a molecule, right? You can model. I mean, doing some operations, you can model the relevant physical properties of this molecule using this Hamiltonian. Okay, so for example, this H it models the energy, right? So it models the total energy of the system, and so it's local because usually the interactions are local, right? So it's like, so each pair of particles, they interact with each other, right? So yeah, I don't know, for example, if you think of electrostatic forces or something, then it's between pairs, right? So and so yes, this quantum Hamiltonian would be a generalization of that, of these, for example, electrostatic forces, when now you have quantum effects as well.
question. So you use the term tensor networks. So is this just an expression of different networks? Is it like just that circuit where you the output of tensor the gate is fed to the next gate? Or sorry, what do you mean by that tensor network?
Okay. So the definition of a tensor network is just it's a graph. So it's a graph where each node. Okay. So here this is a node where each node is labeled by a tensor. Okay. And the rank of the tensor, if you want, or not the rank, the dimension of the tensor is the number of wires that are coming out of it. Okay. So for example, this guy would be a 4 tensor. This guy is a 1 tensor, etc. And yeah, a tensor network is a graph with such nodes. And so here, this is a tensor network with no open edges, right? So that's why it gives a number at the end, right? So if I leave some open edges here, for example, let's say I leave an open edge here and here, then at the end, if I contract everything, it will give me a 2 tensor with these 2 legs, labeling the 2 indices of my tensor. Okay, but here it's just a number because everything is closed. I think, yeah, this really depends on the specifics of the architecture. It's
You know some examples? What are the physical phenomena?
I mean, yeah. So you mean for the gates itself? So let me see if I can say something useful on this. No, I think I can say, yeah. Well, let me skip this. Yes. Sorry.
Inside the gates, there is the equation logic, or lands, or
No, sorry. It's one physical implementation.
The question was what about the physical implementation? Yes, but I don't think I can answer effectively this, so let me skip it. Yeah, precisely.
You have in mind a simple problem which requires 2 to the n complexity or operation in classical computing and require only n operation in.
I mean, I think you mean a problem of I mean this dynamics is typically one of these. So right, so yeah, you're given some quantum model like this, so a Hamiltonian like this, and you want to evolve it for some time. And
this problem is just because the architecture replicates physics.
Yeah, I mean, so yeah, your question is this is a quantum physics problem, so it's not interesting. You want yeah. So I mean, so there is the Shor's algorithm, right? So I think the best example for this is Shor's algorithm. So this has nothing to do with quantum mechanics a priori, but yeah, this is a setting where it's really exponential difference.
So the problem is factorizing an integer to p.
Yes, to p and q. Yes.
And then the algorithm consists in using some linear algebra, something that can be implemented on quantum.
Yes, exactly. So I mean, if you want at the end, the Shor's algorithm is of this form, right? So it tells you what gates to apply, and so it tells you okay, you should apply this gate, then this gate, then this gate, etc. And then you should measure, and then what you will see is that with high probability you'll get one of the 2 divisors of the number, right? So this is I think this is the most important.
So how many qubits do you need to
yeah, sorry, I didn't answer to this question. Yeah, so okay, so okay, if we didn't need error correction, right? If you I mean, if everything was perfect, and if you want to, so okay, so there is an RSA. There are RSA numbers, right? Where these are challenges where you have to factor it. And so yeah, if you take one which is very far from what we can do classically, think with the quantum computer was around 4,000 qubits, you could do it. But now if you add the error correction part to it, this adds a very significant layer. And so there are lots of works even that try to estimate this. And I think the most, so I think there's a paper saying breaking RSA or factoring RSA, I think it uses of the order of millions, like maybe 20 million qubits. And I think there's even in the title the number of hours. I don't remember off my head, but yes. So yeah, that's why we're very far. And actually, so my area of expertise, I didn't talk at all about my work in this case. This is all general. I work actually on error correction in this, and so I'm designing better methods that reduce this overhead.
If I got the idea of it, the idea is we need first to write the quantum algorithm, and then like define how the gates are connected.
Yes, the algorithm is exactly to say what are the gates that you apply. I mean, this is the algorithm. I mean, the quantum algorithm is this. It's to say that between qubits 1 and 3 or 1 and 2 here, I apply this unitary, etc. So.
Yeah, so his question is the circuit algorithm dependent. The circuit for pure algorithm is not.
Of course. Yeah, of course. I mean, yeah. So this is the same as classical. So for every problem, you would design a different algorithm, of course.
No, different circuits. For every algorithm.
But with this, I don't call it an algorithm. I call it a problem. I mean, so but so a problem like factoring for me is a problem, not an algorithm. And yeah, for the factoring is a problem, and for that you have a quantum algorithm, and for me, quantum algorithm and quantum circuit are the same thing. So
just a representation.
Yeah, because I mean, unfortunately, in the quantum world, this is. I mean, yeah. So as I said, we don't have a high-level language to talk about algorithms. I think this is an interesting problem.
Quantum computer, Amazon.
Yes.
The quantum computer for solving certain problems.
No. They're general. You can apply arbitrary gates, so you can come up with your own quantum algorithm like this, and you can just tell it. It will run it.
To simulate, or is it constructed with?
This I can't guarantee, but because but okay, I think okay, if we trust them, then yes, they are doing it on a real quantum computer. Yeah.
I have another question. So to come up with this new algorithm, for example, show algorithm, so do you think differently from the classical algorithm to factorize an integer, or we start from the classical algorithm and then we
so yes, so definitely there are some. So Shor's algorithm is not very simple. It has several parts, and some parts are purely classical. So
starting point of the classical algorithm to factorize.
I mean, I wouldn't say that you take a starting classical algorithm and you and you just modify some part, but you can do some. For example, here classically, you reduce it to order finding. Okay, this is a standard thing from factoring to order finding, and so then you focus on order finding and you do the order finding on the.
Quantum level is
At the quantum level is different. It uses some classical algorithms inside it, but yeah, it's different.
So there is no other questions. I'm trying to